So I would like to first start by letting the panelists to comment or question each other's work, if they like. You can't do that, so maybe I question then some of the work, so that we can have some discussion. You know, I really like all of these devices that you guys are presenting. I mean, it is really good and interesting. But you know, for instance, when you look at history of various fields of science, like communications, it led to a lot of algorithms, theories, information theory, digital comm, lots of fundamentals. Or say imaging, it led to inverse problems, Tikhonov theory, or optics led to nonlinear PDEs. What do you think that these kind of efforts would lead to? I mean, would there be any fundamentals, or would it be just implementation and old techniques being implemented in these devices? Anybody wants to take that?
I'll take a crack at it. So I think what's interesting about sort of monitoring patients is that, you know, what we're dealing with is sensor networks, right? Sensor network is an old concept. At least the paradigm is well appreciated. But what's interesting, I think, is that the physical systems that we're trying to model are becoming more and more complicated. And what I see from an algorithms perspective is that means that we need a real emphasis now on not just sort of signal processing, so signal analysis and synthesis. It's really a problem of how do you model this system, particularly when you don't understand it too well at a physical level. And so I think, you know, what I really see as an opportunity is that there's this very generic problem of modeling a complex system that we probably don't have that great a shot at understanding the physics of. And so there's these techniques. We happen to be focusing on data-driven techniques, which help you to some extent circumvent the physics and sort of figure out how these algorithms can be integrated and sort of deployed in networks that are able to really treat data as a much more valuable resource than just a way of observing the system.
Anybody else wants to comment?
This is along the lines of the famous Rumsfeld one-liners. Typical of any R&D program that you start to look into. It's a problem, right? It's one of those things that we know what we know, and we don't know what we don't know. And what we know maybe will lead to something that we don't know. What that means is we're looking at this because there's a need. Everything from miniaturization, little things, to the wireless communication, anything. And it starts with maybe an applied research, right? Because you're taking things that you know, and you're putting them together to solve a problem. But along the way, you find a hole for which there is either a solution or it leads to an area where it needs investigation. And out of that, who knows? You will find some things. I mean, look at the space program. I mean, right? I spent many years doing NASA programs. And John, you know this as well. You know, we got to go to the moon. Okay, you need rockets, you need this, you need telemetry, you need propulsion, etc. Let's go put them all together. Whoops, didn't work. What's the problem? Well, you know, there's something about the nozzle, and you know, up to a certain level, and it explodes, and didn't know what was going on. You need materials. All of a sudden, this whole idea about reentry opened up the new resources into materials research, and guess what came out of that? Not just for NASA. I mean, look what's happened here. Even in the field of wireless communication, look at the telephones that we have, the original cell phone. Remember Gordon Gekko, you know, that movie, Big Cell Phone? And now, I can do so many things with this little device, and guess what? It's getting more powerful. People are looking at battery. There's a lot of battery R&D going on in terms of improving the performance of the battery while reducing the cost and the size. So, again, very good example. We need to have batteries. Do we have anything? Yes, you use the current batteries. Well, maybe there's a new thing. Let's find out if there's a way we can come up with new materials or new battery technologies. So in summary, what I'm pushing for is it's one of those loops. Let's start with what we know, what we want, and it's R&D, right? At least at this stage. Let's not be afraid of going outside the box. Let's go into the unknowns, right? Again, Star Trek, right? Let's go where no one has gone before. So.
Thank you.
Want me to make? Oh.
But what we saw here, at least today, was that, for instance, in the standards, the same old communication techniques are used, right? So what do you say to that? I mean, if it is something that is fundamentally different, why are we first visiting it this way? Do you have any comments?
At least for the part that we are doing like channel modeling for inside the body for localization application. I think it's a very, very interesting scientific question, because nobody has discovered the body for localization in one hand, and on the other hand, people are designing these micro robots they're sending inside the body to do surgeries. So localization becomes like an important issue, and inside the body there is nothing in the literature. Now what is different about inside body? I mentioned 2-3 of them in there. Infrastructure is moving. Okay, and then usually you go either for blood circulation system or digestive. So it's a sort of guided like medium that you can take advantage of that to the. I think this is a very fascinating problem, scientifically from the point of view that you was, and if we have that knowledge about radio propagation, which does not exist right now. I mean, radio propagation is not the issue, it's the issue of waveform propagation. When you apply that for different applications like localization, using time of arrival, direction of arrival, I see it like a very, very good area of research which can do fundamental things. Good PhD theses out of that, a lot of citation to come out of it. That's for my program, I think. But
I'll pick up.
sure.
I think that some of the challenges we've got is we're trying to tweak out every last bit of performance to try and achieve the goals. The smaller device, the smaller the battery, and so the less power you've got to work with. So these, development of new standards is okay, but we've got to make sure that those standards are flexible enough to be able to give the people, the designers, the flexibility to be able to implement their own solution. We went for a 950 megahertz approach for this. There was Bluetooth, we did this a few years ago. There was Bluetooth around, but when we analyzed it, it wouldn't meet our power requirements to have that overhead in there. Now, I know there's been some improvement in the standards, and maybe we should relook at those. But when you're trying to, again, tweak out every last bit from these very small, and yet you want them to be very powerful devices, I see the challenges of being, the problem we've got, I think, is everyone's having to come up with an ad hoc solution just to be able to make it work.
Any other comments?
I think imaging, remote sensing, and communication, basically, they are pretty similar. Electrical engineering are built upon a few fundamental techniques. We just apply it to solve different problems. To me, imaging, communication, and remote sensing are pretty much the same. You can use the same technique and publish in these several different journals if you want to. So it doesn't matter whether we're applying communication techniques to solve problems in other domains, because communication techniques are also stem from just a few techniques, that fundamental techniques that electrical engineering are based on.
Any other comments? So
I
want
to comment on that problem.
Okay, go ahead.
I had a person actually from Qualcomm once told me that, because we are talking about wireless access and localization, he said wireless is application and propagation. We have a bunch of algorithms for localization, bunch of algorithms for communication, but we go from cellular to wireless LAN. What does it change? Channel. The way that signal propagates absolutely is different. But now I have a lot of multipath. Then I take local area networks. Now I go to a small inside the body. Again changes, because application now, moving infrastructure, non-homogeneous, etc. So I think fundamental, maybe I'm biased toward my area of research, but fundamental in wireless always have lied inside radio propagation. not just for antenna design, for waveform transmission, to fit different algorithms which are like CAN in there. But every like 10, 20 years, somebody comes up with a space-time coding with like MIMO every like 10 years or something. But application changes, radio propagation always exists in there. That's my humble opinion.
There's no doubt that radio propagation, all of these things are very important.
Yeah,
I'm just asking that
but it's
what
new.
do you think that there's a fundamental, or is there going to be a fundamental waveform like a soliton or something
No.
for these propagation models, something that is unique
Yeah.
to this kind of application that people can build on?
Yeah,
That was the question I was asking.
My point is that if we understand the radio wave, signal transmission, then we can discover new waveforms. Then we can compare the waveforms. For example, for indoor geolocation, people started at the beginning 20 years ago. Everybody had solution. Government so far has spent over $1 billion on that. Not you, but other people. DARPA spent a lot of that. But still, we were doing radio propagation. Multipath doesn't let you to do that. I think that was one of the valuable things we could get out of it in here as well. Yeah.
So now
There
I'd
is
like to
question.
open the floor to some of
There
the
is back.
general population here. So please go ahead.
No, there's
Okay, one thing, I don't want to cold air on anybody here, but in our studies of body channel, it's a lot worse than you think it is, and then whatever you think, it's even worse than that. Because any RF engineer that starts with a Maxwell equation and looks at the mu and sigma of the human body, it's different from one spot in a body to another. A bone is different from fat, and muscle is different from the other. So your waveform and propagation may be good for the next quarter inch of transmission, but the next half an inch of transmission may be different. And we found that the research that probably should be done on the basic level is Maxwell equation for non-homogeneous medium that isn't single epsilon sigma mu, but for ones that change through the body, and that's the big difference.
Any other comments?
So-
that problem, there's been a lot of work done with buried antennas. The Cold War, as you know, the Soviet Union had them. We had them all over the place in the United States. The Chinese had them. And there's a huge body of knowledge about antennas and matter, and in homogeneous matter, and isotropic matter. So I think a lot of that could be applied to the human body. There's, stuff in the 50s, 60s, and 70s probably we've forgotten about. Old stuff. There are textbooks written on this subject. Like. I'm saying it's non-homogeneous. The earth is the same as the body. The earth is not laterally homogeneous or vertically homogeneous. Neither is it isotropic. And so you run into the same problems when you try to predict the strength of radio waves in the earth and their dispersion. And there's just a huge body of knowledge about that. Also in prospecting. There's a lot written about radio propagation in the earth for looking for things, oil.
Well, I can make a comment on that. I absolutely agree with you. I believe somebody told me writing is rewriting. And research is research. So we are always searching things that have been done in the past. We added something. And when we add it, there is a window of time that people are sitting down there and they want something to come out of it. So a lot of things has been done in radio propagation inside body for localization application. There is nothing in the literature, at least for our part. So we are going and researching.
I'm just saying you could maybe learn by looking at what's been done
Yep.
in the earth. Second question, what about cadavers? You keep talking about you can't make measurements. Why not cadavers? I mean, I worked on a project where we did that. Cadavers, dead. Yeah, but I mean, can't you get at least some information from implanting sensors and making measurements? Okay.
So I want to actually ask some of the last questions, please.
But the response, the other thing, problem with cadavers is that the dielectric property changes after the person dies. So unless you do it very quickly, it's not the same. One challenge that I didn't see it emphasized enough throughout the day is security, specifically the encryption. And that goes to the root of the problem, which is power. So I feel that if there is any fundamental issue, that's a very good question. It goes back to the limited power budget. So we have a limited power, very, very small power. We want to provide communication, we want to provide security, we want to provide how can we do this? Is there a study that, given this much power, what is the level of security that it can provide? With communication, how long can you sustain it? It is not going to be pleasant to recharge an implant very frequently, or have to be in close proximity of something in order to establish communication link. So mobility and global accessibility is an issue, but then the power is tying us down, the power budget. So.
Necessarily encryption throughout your whole system there, and I've always debated, do you need it from the the implantable sensor to then whatever's picking it up, or then can you encrypt it from then on?
If your actuators inside the body, then you're opening yourself up to malicious attacks. Yes.
Yeah.
So for that, you need a strict security. And that would be a big challenge. I don't see. Although it's not my area, but I see the need for it, and I've been pushing everywhere that I go that there needs to be a fundamental study on the security levels.
Which is not that energy consuming. In order to get into some other topics, I just try to be devil's advocate. So I push some other discussion. One of the presenters started talking about, for instance, seizure and EEG waves and spinners. I believe it was you. And that we want to recognize this. This is a non-stationary learning problem in general. It's not a typical VC dimension, statistical learning that you could have theorems proved, or it varies from one person to another person. You have 2 drinks or have a coffee, your spindles or waveforms will all change. So, and there is not really any ground truth. I mean, even when the doctor says that this is a seizure, there may be a slight seizure that nobody knows. How would one even know when you build such an algorithm that this is something that is verifiable in practice?
Yeah, I think you're right. And I don't think there's, at least in my study, there's an answer to that. But I think what is important is recognizing that we've got some clinical expert, for example, who can provide some input into diagnosing this. And the issue is that resource is highly constrained. And so the question here is not necessarily how can we verify it beyond what that clinical expert can provide, but really how can we leverage maximally the knowledge that clinician can bring. And I think that there is a role for algorithms to play and technology to play in at least presenting that resource very selectively with data, and then sort of deriving or taking advantage of the knowledge that resource can provide into building a system that can provide support. So it's really, our study is one of taking that resource and leveraging it so that it can be applied much more scalably. But I definitely agree that it would be great to improve the ability to diagnose and recognize these correlations that are clinically important.
But should a computer at the end diagnose? That's a fundamental question, because, I mean, you get two doctors, they will be having two different opinions. Yes, please.
Can I make a comment and then pass it to Chris? Sure. I just want to share a quick story with you guys. The Undersecretary for Science and Technology at DHS is a medical doctor herself, Dr. Tara O'Toole. During the first review, when she first showed up at the scene, we discussed various programs. And many of you by now know that PHASER is a program I started at S&T for the emergency responders to pretty much answer all the questions and comments and issues that you've brought up. That is, how do we monitor what's happening to them? On my first slide, I got stuck. And immediately when I said, yes, we are looking at the health, the well-being of the first responders, and this type of technology has a lot of application, not just to the 2.5, 3 million responders, but the general population, and you can extrapolate healthcare, reduce the cost, return on investment, all of that. I said the second word, and she said, are you telling me that you are going to be able to predict heart attacks? And before I even said anything, she said, what the hell are you doing? So there was a lot of back and forth, which really ended up redirecting. Again, you know, how do you know that you're researching, that you're developing something? I don't know. We had to redirect and say, listen, we're not about prediction. We're just about monitoring. And the whole number of issues that it brings up that I think you want to say something about, right?
I think if we're going to try and develop higher models of physiological data that can be useful in detecting clinical events, then we've got to validate the system by collecting those events. And that is no easy task, particularly if the events are rare. But it has to be done, and the way to solve that problem, I think, is to set up a network system that can collect vast amounts of data and to train that system so it becomes an intelligent system. Having said that, I fully agree with you. If you put two physicians together, they'll have a difference of opinion, and there are very seldom absolutes in medicine. I mean, even myocardial infarction is not an absolute because, you know, it's sort of reflected by varying degrees of elevation of cardiac enzymes. But, you know, what is a heart attack and what is what we call a myocardial leak?
Any other comments? Here, yes.
I feel what we're talking about is an extra filter to healthcare. At the moment, if I have chest pain, if I can be bothered, I'll go to the doctor. Unless I get really scared, then my wife will tell me to go. I think with technology, we can actually have an extra layer and tell you we're worried about you, and that'll motivate you to go to the doctor. I don't think we're replacing the doctor. I think we're adding something that can cover the whole population. My second point is I think, you know, there's remote arrhythmia detection centres now that are doing pre-filtering, and it's the graphical user interface that's having humans, cardiac technicians, that are then reporting and sending summary to doctors. So I think there are predicates for this, and I think as we go further and further out, you know, there's beautiful use cases that are working right now. It's not a replacement, it's extra, and it gives medical treatment to everybody.
One of my biggest interests in this is, in addition to understanding what the state of technology is, based on what was discussed today, to get an idea, if you will, even validate or verify several questions like, what is the state of technology? What gaps does this community, does this group feel like they are the technology gaps that require additional research? And by research, I mean just a broad spectrum, anything from basic research all the way to applied and so on. And then the final question is, it is my opinion, this is just me, that this is a very, very growing area. It's becoming really important because it's an enabler for a lot of different topic areas. Does everybody feel the same?
Is there any other comment? Because if there's none, in the interest of time, I want to thank all the speakers. Is there any other comment? So, yes, please. Last comment.
Last comment, and it may not be coherent. Just a couple of thoughts. Having myself been involved in wireless physiological status monitoring back in 2002, 2003, we were asked by Department of Defense, working with the Natick labs, to try to create a warfighter physiological status monitor. We did a lot of analysis and really convinced ourselves that if you're not measuring respiration rate incredibly accurately, you cannot really determine health status. I mean, the point was made, if you're upside down, that's probably a bad sign. But I think that sometimes paying attention to the basic parameters, and respiration is an important one, can enable us to determine health status a lot better than if we just have, say, heart rate and one or two other things. And to that end, I'm believing that if health status assessment, rather than the presence of acute illness, might be a big goal of the work that we're doing, I just commend the remote sleep lab sort of use case as a really good place to invest more effort. And anybody can talk to me a little bit about it later, but I think that it's an environment that's sort of midway challenging. You know, you're not running up a mountain. There is power available. There's a lot to be learned from the study of sleep. And I think there's something to be said for picking a focus area for additional work, and I would just commend that one for no particular reason than it just feels on a gut basis like a right thing to do.
So obviously, this is a very growing area, and it has a lot of future. There are a lot of fundamental questions that we don't know what they are, and some that we know what they are, that we will figure out, hopefully. And there are a lot of issues that need to be studied. I just want to thank this panel for this great set of presentations, and for this very lively discussion. I want to thank everybody. And I'm going to pass the microphone to Professor Pahlavan, who is going to give the closing remarks.